So consider the three-periodic Poncelet family, this blue triangle, inscribed in an outer circle, the black circle, and circumscribing an inner concentric ellipse, the brown ellipse, also known as the caustic. Okay, so here's the three-periodic Poncelet family, interscribed between the outer circle and the inner ellipse. Of course, the circumcenter x3 is stationary at the center. Okay, I want to talk about the concept of the power circles of a given triangle. So I'm going to locate on each one of the sides of this triangle their midpoints, and I'm going to draw three circles, each of them centered on a midpoint. For example, O1 is the midpoint of side P2, P3, and I want the circle centered on O1 to pass through the opposite vertex P1. Likewise, I want the circle centered. So let's see if we can see that circle. So you can see here that there's a circle passing through P1. Okay, passing through P1, going all around, and centered on O1. Likewise, I want a circle centered on O2, passing through P2, and one centered on the midpoint, O3, passing through P3. So we're going to get a group of three circles, and I can watch them as I traverse the family. Let's do this slowly. So there are the three so-called power circles, and this definition is valid for any triangle. Just take the three midpoints and draw the three circles passing through the corresponding vertices opposite to that midpoint. So we get this family of three circles. Interestingly, over this Poncelet family, the family with circumcircle, the sum of the areas of these three circles is invariant. So if I change, for example, the relative proportions or the aspect ratio of the inner ellipse of this family, okay, I'm going to get a different family of circles, but still the sum of the areas of the three power circles, though here's the area of the first power circle, okay, this area is not constant, but the sum of those areas is. So that's pretty interesting. A second Poncelet family where this works is the homothetic family. So let's turn off the power circles, and I'm going to draw the homothetic family. Let's zoom in a bit. So what's the homothetic family? I have two concentric axis-aligned ellipses where the inner ellipse has semi-axes which are half-sized those of the outer ellipse. So you get this three-periodic family. This family of triangles preserves areas. As you can imagine, it is an affine image of the Poncelet family interscribed between two concentric circles. So this family here is the affine image of family of equilateral triangles interscribed between two concentric circles. We can talk about this affine image. Now, as you know, the concept of the circumcircle is not invariant under affine transformation. So when I do draw the three power circles, okay, these power circles, they do not commute, they are not equi-invariant with respect to the three power circles in this case here. And yet, when you do go to a homothetic pair and you compute the three power circles and you animate that, you're going to notice that, and let's scale this down a bit, you're going to notice that the sum of their areas is invariant. So you get this invariance for the homothetic pair and the pair with the circumcircle. Both of them produce total power circle area sum invariant. However, if you go to, say, the confocal pair, the elliptic billiard pair, okay, you're going to notice here that the sum of areas is not invariant. So this does not work for the confocal pair. This does not work for a pair with an incircle. For example, this one, the sum of the areas is not constant. And this does not work for the dual pair, where you actually have two homothetic ellipses, like so, but the inner one is actually 90 degrees turned, rotated with respect to the outer one. So here the sum of those three power circle areas is not invariant. So you need to be, again, in the circumcircle case, invariant, or in the homothetic case, invariant. And maybe there are other pairs, maybe there's a rule for which this invariant manifests itself, but At the time of this video recording, we do not know what the rule is, and we do not know if this property is trivial and how to prove it. If you have any ideas, do let us know. Thank you very much.